Welcome to Pomodoro Joe for Sunday, June 25th, 2023. Today we're looking at LeetCode problem 1575, count all possible routes. This is a hard problem. So in this problem, I'm not going to read this whole thing. Well, maybe I should. Okay, I'll read the whole thing. So we're given an array of distinct positive integers, locations, where location index I represents the position of a city I. You are also given integers start, finish, and fuel, representing the start city, ending city, and the initial amount of fuel you have. At each step, if you are at city I, you can pick any other city, j, such that j is not equal to I, so you can't go from the same city to itself, and then move to that city. So you can move to city j. Moving from city I to city j will reduce the amount of fuel you have by the absolute value of the location of city I minus the location of city j. Please note that the absolute value did blah, 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 okay? Notice that fuel cannot become negative at any point in time, and that you are allowed to visit the same city more than once. That includes both the start and the finish cities. Return the count of all possible routes from start to finish. Since the answer may be too large, return it modulo 10 to the 9th plus 7. Let's put 25 minutes on the Pomodoro timer and we will get started. So my plan with this one is to do the simple thing first, and we will do a recursive solution. So for this, my plan is to start at city start, then we'll just go to every city we can get to, which in this case is actually every single city. So this is kind of like a graph problem, but we have connections to every single city. It's just those connections will have a cost, and that's the amount of fuel it takes. So we'll go from start to every other city, check to make sure we have enough fuel. If we still have fuel left over, then we'll go from every other city to every other city until we reach the final city, which is our finish. Now, even when we reach the finished city, we can keep traveling. If we still have fuel left, we can go to every other city connected to finished city, and we can always go back to finished city. So this gets a little bit complicated. So let's just think of this recursively. So if we have this function, count routes, now, if we have this function that takes a start and a finish, and it will return the number of ways we can get from start to finish, for now, let's not worry about how it does it. Let's just imagine that it does it. So if this function works, we can go from start to finish, and it returns all the different ways we can get from start to finish. That's great, because we can start at start, go to all the other connected cities, reducing our fuel by the amount of fuel it takes to get to those cities. And then from those cities, we can ask, how many routes are there to get to the finished city from this city? So we'll have to update our fuel every step along the way, but we can add all of those different routes up until we get our final answer. Let's see if we can explain this with some code. So we'll have a recursive function here. So def count routes recurse. So for this one, I will take the starting city, and I'm actually going to call this start city because the city and the location are different, as we noted here. The city is the index and the location is the value. So I'm going to call this start city so that we know that it's the index and not the location. And we have the current remaining fuel. So that's how much fuel we have left. Now inside of this, we will pull out the different locations, but for now we'll just start with our start city and our remaining fuel. Okay, and we will have an internal result. We'll set it to 0 to start. So this will be the number of ways we can get to the finished city. We'll start it at 0, we'll add to it, and then we'll return the result when we're done. Let's start with our base case here. What's the base case? Well, I guess there are kind of two base cases. One, if we're out of fuel. The other, if we are at the finished city. Although the finished city is not really a base case, and I'll explain that in a second. So the first base case, if we're out of fuel, we are done. We cannot travel anymore. So if our remaining fuel is less than 0, we're out of fuel, we can't travel anymore, we'll just return 0. There are no ways to get to the end city with no fuel left. So next one, if the start city is the finished city. So if the start city is the finished city, well, now we've got one way to get to the end. We've made it to the end. So our result will equal 1, but we don't return. Just because we're at the finished city doesn't mean we're done. If we have fuel left, we can still drive out to other cities and come back to the finished city. That's what this was saying here. We can always go back to the city more than once. So we can visit any city more than once, including the start and the finish. So just because we're at the finished city doesn't mean we're done traveling. but we do have one way to get to the finished city, so our result will be incremented by 1. All right. Now we go through all the recursive cases. But before we do that, I actually want to get my location. So the start location. Well, that's going to be the locations at this start city. Again, this goes back to this city not being the same as the location. So the city will be the index, the location will be the value at locations for that city. So the start location will be at the location start city. Now we go to every single other location. So basically for every location in locations. Okay, I actually probably want the city as well. So let's do this. We'll call for every end city or next city in locations, and we'll enumerate our locations. So enumerate will just go through this iterable and return both the index and the value. So the index will be this end city and the value will be this location. Okay, so from this city, this start city that we're at, we'll go to every other city we can go to. We'll figure out how much fuel that costs us, and then we'll recurse to all the other cities. So let's calculate our remaining fuel here. I guess I'm already using remaining fuel, so let's call this the new remaining fuel. And that was told here, it's the absolute value of our locations. So we will use the absolute value of our start location and this location minus this location. So now that we have the remaining fuel, we can start doing our recursive calls. Basically from this point, we'll just go through every other city we can get to if we still have fuel left to get there. Now we'll figure out if we have fuel left to get there when we do the recursive call. If we have less than 0 fuel, we didn't have enough fuel, so we'll just return 0. Now one caveat here, we cannot go from one city to itself. So for example, that tells us here, as long as j is not equal to I, we can travel to that city. So we do have to make sure that our end city is not the same as our start city. All right, so we check if the end city is equal to the start city. If it is, we cannot go from that same city to itself, so we'll just continue. That one doesn't count. Otherwise, basically we need to increase our result by the number of ways we can get from this end city to our finished city. So we'll just call our recursive call. So our result here will be increased by how many ways are there to get from this end city with this remaining fuel to our finished city. All right, where's my remaining fuel here? So that will be enough there. Let's swap these. We don't need to calculate this fuel if we are at the same city, so that will save us a little bit of computation if we do this continue first. Okay, that's a little bit better. Out here, we will need to return our result at the end. Now, we probably want to do our mod at this point. So we do need to return our result modulo 10 to the 9th plus 7. So let's actually create a mod value out here. And that's just 10 to the 9th plus 7. So we'll return our result mod value. All right. And now, before we can complete this entire solution, we do need to make our first initial call to our count result recurse. So our result out here will be count result recurse. We're going to start at our start city, and we will have fuel to start with. And then we will return our result at the end. But we might need to, well, we're already doing the mod here, so it should be all right. It's possible when we do these adds, we'll be adding things that are very close to the max, basically as close to this mod as you can be. So this result might actually exceed our mod value as we do these adds. We might want to do our mod here as well. Let's just put it that way. Well, we'll start with this and see how it goes. All right, so I think this should do it. We've got our mod value. We've got a recursive function here. It's going to take the start city and however much fuel we have left, our remaining fuel. If we don't have enough fuel, we'll return 0. If we are at the end city, our result starts out as a value of 1. Then we'll just go through all the remaining cities, seeing how much fuel it takes to get to those cities, and then counting the results to get to that final city here. Okay, so this should work. Let's try it. Maximum recursion depth exceeded. Ah, right. All right, so we have our start location. This is just the location of our start city. Our end city and location, we'll go through every single location we can, grab the end city. If it's the same as the start, we move on. Now our new remaining fuel, that is actually our remaining fuel minus the cost. That's the absolute value of the start location minus the end location, or this end city location. So it's the remaining fuel minus this amount of fuel, the cost of the fuel. And then we can move on. Okay, that's my mistake there. Let's try this. Okay, so this works. Now we'll submit this. It's probably not going to be fast enough, but there are things we can do. Okay, time limit exceeded, and this was a very short number of locations. It's only 4 out of 109 test cases passed, so that's pretty bad. We might need to find a completely new solution. All right, we'll add this test case. So the simple fix here, or the simple thing to try here, is because these are simple inputs, this is just an integer, this is just an integer, we can actually use caching to solve this problem. So this is a function decorator. At cache, you put it before your function. If the function has simple arguments, now this will not work with arrays or dictionaries as input arguments because those are referenced variables. It can only work with simple IVRs. So this will significantly help. However, it might not be enough. We'll find out. And that is enough. So that caching saves the day. So we beat 71% for runtime and 17% for memory. That's awesome. Now I'll jump back really quick in case you feel like cache is cheating. I'll show you how to do this with some dynamic programming. Let's remove the cache. So now again, this should fail if I just run this. So without the cache, we exceed the time limit, we fail. So instead of using cache, one other option is to use dynamic programming. So we'll use DP. Now this is a very generic way to use dynamic programming. This is also called memoization. So we'll keep our own internal cache essentially. We have a dictionary. So this dictionary will just be our own sort of internal cache. It will hold on to the return values for every set of input arguments, which means our key is just the input arguments and our value will be the return value. So you just create a dictionary out here, we call it DP, and in here, we can create a key. Now the key will just be a tuple of our input arguments. So that's the start city and our remaining fuel. Next, we just check. If this key is in our DP, then we can return the value that's stored there. That's super simple. If the key is in the DP, we return it. Otherwise, we have to go through and find every place where we do return. So that's here and here. Those return values need to be cached. So first we'll go here, DP for this key. Now, since I've created the key at the top, I can just use the same key. That's going to equal 0 because we're returning 0. Now down here, we can say DP at key is equal to this result mod val. And then we'll just return our DP at key. Okay, it's that simple. We create a dictionary out here. The first thing we do is check to see if the key is in the dictionary. If it is, then we can just return the return value. If it's not, then every place where we have a return, we just have to set that value in our dictionary. So this is our own version of the cache decorator. Okay, that seems to work. Let's submit this. Typically, this will be slower than using the cache decorator, but let's just see. Yes, and we pass, but it's significantly slower than using cache. We only beat 23% for runtime and 20% for memory, as opposed to 71% for runtime and 17% for memory. So using the cache decorator is preferable. Not only that is it's pretty standard, so if you see that in production code, you'll know what it is. Whereas if you see something like this in production code, you have to go through and make sure that it's doing what you think it's doing. Okay, well, that is it for me. Again, this was LeetCode problem 1575, count all possible routes. All right, well, I hope you enjoyed this. Hope you had fun. Hope you learned something. Hope you can go out and write better code.